The last big thing I really want to talk about in this section is how to name coordination complexes. And we haven't talked about these so far, but if you're ever in the outside world and you see one of these names, whoa, they look intimidating. They're usually long and they've got weird symbols in them and stuff like that. So I want to have a quick introduction to how to name coordination compounds, and they're not too bad. Like all compounds we've seen in chemistry so far, it's always cation first and anion second. Cations are first, anions second, but if there's a metal in the anion, it gets an ATE ending. And I'll show examples of all of this here coming up. This is kind of the boring rules part, okay? Ligands are named first in alphabetical order, so ligands before the metals, all right? Most ligands will have an O ending, but if you have multiple ligands, you have to use Greek prefixes, di, tri, stuff like that. The metal atom or ion is always named last, and the metals always have the Roman numeral oxidation state following them. And that's not always the case in some of the compounds we've seen, but anyway, if you do need one, it does need to be included in these coordination compounds nomenclature rules. This is the weird part. You don't want to put any spaces in the complex ion name. So some of these names can go on for a long time and they look really weird at first, but trust me, you can do this. I do have a coordination compounds handout in the companion and also online, and I encourage you to check it out. It's got some examples of how to name these things. They're not too bad. The ones we're looking at are pretty chill. And again, I just want to kind of introduce this so that if you do see them in the future, you won't be intimidated. IUPAC is the official group that creates the rules, if you will, for these different names. And neutral ligands are usually referred by their usual name, but there are some exceptions, okay? And these can be a little strange. Water, if you see it in one of these complex ion names, is referred to as aqua. You don't call it water, you call it aqua. And ammonia is really weird. If you have ammonia in one of your complex ions, you refer to it as an amine. Now I want to stop right there. Amine in this then is AMMINE. And we've already seen in organic chemistry that you can have an amine, which is when you have a nitrogen with an alkyl group R and maybe another alkyl group, another hydrogen. Those are AMINE. So an amine in organic chemistry is different than an amine in coordination compounds. In coordination compounds, you'll spell it with two M's and it means ammonia. In organic chemistry, an amine, like ethylene diamine, would be just a single nitrogen with at least a carbon on it. Okay, carbon monoxide is called carbonyl. This is another one that's strange. Carbonyl in organic chemistry was a carbon-oxygen double bond. So for example, ethers had alkyl groups on both sides of the carbonyl. That was cool. A carbonyl in this stuff is just a carbon monoxide. So it's a little bit different rules for a little bit different nomenclature system. Just think about that as we go through it. Hydroxide becomes hydroxo. That's weird, but I can dig that. Some ligand names already have a Greek prefix in them. So for example, ethylene diamine has di already in it. If you had two ethylene diamines, it would be diethylene diamine. And that sounds weird. Like, do you have two ethylenes and two amines? Or is it two ethylene diamines? So if your Greek prefix or if your ligand, already has a Greek prefix, then what you want to do is use the alternate prefixes. And these are bis, tris, tetrakis. So for example, if you do have two ethylene diamines, you don't want to call it diethylene diamine because you're not sure where the di is referred to, etc., etc. What you would do here is call it bis ethylene diamine, and bis is just an alternate form of saying two. Tetrakis is 4, Hetrakis is 6, etc., etc. Let's look at some examples. These things get really weird. So let's say we wanted to name this thing. It's cobalt. It has 6 waters and a +2 charge. Water is neutral, all right, so it doesn't affect the +2. So the +2 literally is the charge on the cobalt. We name the ligands first. The metal comes after it with its Roman numeral. And there's 6 of the waters, so it's hexa. And if you remember from the previous slide, water is aqua. So this thing is hexa aqua cobalt 2. It's the hexa aqua cobalt 2 ion, if you want to be official. All right, all one big word, no spaces. Water is called aqua. Hexa is the Greek prefix for 6. Hey, you've done your first coordination compounds nomenclature. All right, woohoo. Anyway, let's do another one. Now, this crazy thing has a platinum. It has 2 ammonias and 2 Cls, all right? So this one, we have 2 types of ligands. We have ammonia, which gets that weird amine name, and we also have 2 chlorides. Most of the normal monodentates, you replace the chloride by chloro. If you have a choice between amine or chloro to go first, you go at alphabetical. So this would be diamine, all right? And the other thing is that you'd then put dichloro. And the last thing you would do is put the platinum. But we need to figure out the charge on the platinum. Now, ammonia is neutral. Chlorides are -1, and there's 2 of them. This is going to be a platinum 2 center. And one thing I haven't talked about yet, but in this version of the molecule, notice how the chlorides, the green atoms, are 90 degrees from each other. This is a lot of times referred to as a cis form of this molecule. So the best name for this crazy thing, cis diamine dichloro platinum 2. Okay, cis means that the chlorines are at 90 degrees. If they were 180 degrees across from each other, it would be trans. It's diamine with 2 M's because we have 2 ammonias, dichloro, 2 chlorines, and it's a platinum 2 center. So again, notice here how water is aqua and ammonia is amine with 2 M's, which is totally wild. Here's a molecule that we've bounced around a little bit. This is a copper. It's a copper 2+ because ammonia is neutral and 4 ammonias. So because NH3 is amine and 4 is tetra, you would say tetraamine copper 2 ion. All right, tetraamine 4 ammonias, copper +2, and this is an ion. It has a charge on it, so that's why we put the ion on it. All right. Now, most of the metals in this section are octahedral, but there are some tetrahedral, some square planar all over the place and stuff. So again, with crystal field theory, which we're not going to talk about in this class, unfortunately, you can do more predicting if it's tetrahedral or square planar, but for right now, we'll just go for it as is. This compound has a lot of atoms, and if you look at the structure, it's like, what? But if you look at the formula, all right, NH2C2H4 NH2, that's the ethylene diamine thing. That's a bidentate ligand, and you'll notice that there are 3 of them, okay? So there's 3 ethylene diamines. It's a nickel +2, but ethylene diamine has a Greek prefix in the name. So if you have one of these kind of ligands where it has a Greek prefix in it, that's when you use the bis, tris, tetrakis alternate system. And 3 is a tris kind of version. So it goes bis, tris, tetrakis. So this would be the tris version. So you would write tris ethylene diamine, nickel 2 ion. Good to go. Notice how if you do use bis, tris, tetrakis, you do put the ligand in parentheses when you're naming it. And that makes it very clear that that whole thing you have in this case like 3 of them, etc., etc. Vasca made this compound. Everybody calls it Vasca's compound. Nobody calls it by its real name. What's wrong with them? Anyway, in this compound, we have a chloro, CO, which is carbon monoxide. If you remember, we call this carbonyl. And this crazy thing, it's triphenylphosphine. That's the name of that ligand. That's another kind of ligand in this particular molecule. Now up here you can see, here's the carbon monoxide, here's the chlorine, and each of these purple atoms right there, they represent the phosphorus of the triphenylphosphine, okay? So let's start off by putting these in alphabetical order. Carbonyl is before chloro, all right? Triphenylphosphine would be last, but triphenylphosphine has a Greek prefix tri in it. So for this one, we would also use the alternate system. It would be bis, parentheses, triphenylphosphine. And then finally, we have to think about what the charge is on the iridium. Well, triphenylphosphine is neutral, carbon monoxide is neutral, chloride has a -1 charge, and this compound is neutral. So that must be iridium 1. So this whole thing, carbonyl, chloro, bis, parentheses, triphenylphosphine, parentheses, iridium 1. You can probably see why everybody calls it Vasquez compound and not carbonyl, chloro, bis, triphenylphosphine, iridium 1. Oh my goodness, that's a long name. If you see a long name like that, break it down. All right, break it down into pieces that look familiar. So carbonyl, chloro, there's the word bis with that kind of thing, and then the metal with the ion. Good to go. Let's name this molecule NiNH32Cl2. All right, no problem. So when you do this, first of all, have to put the ligands in alphabetical order. We have amines and chloros, so amine comes first. Amine and chloro don't have Greek prefixes, so we'll just use di. It would be amine first, chlorine afterwards, so diamine dichloronickel, but we do need to figure out the charge on the nickel. Ammonia is neutral, chloride is -1, and there's 2 of them. This must be a nickel 2 center. So this thing would be diamine dichloronickel 2, and that would be the cool name of this compound. Woohoo! Again, if you see a long name like that, just break it down into little pieces, and then these molecules will absolutely fall for you. Here's just some more examples. This one right here, as you can see, a square brackets. This is the cation and this is the anion. So if this was, say, MgCl2, we would call it magnesium space chloride. Well, we're going to call the complex ion first, have a space, and then put chloride after it. So let's deal with the complex ion there first. It has 5 ammonias and a chloro, amine before chlorine, all right? So it would be pentaamine chloro. We do need the charge on the cobalt. Cobalt has a total of 3 chlorides that it's dealing with. So that is a neutral compound. That means that cobalt must be a +3. Remember that cobalt 3 is going to go at the end of the cation, and you'll have chloride after. So this crazy thing, pentaamine, 5 ammonias, chloro for the chlorine, cobalt 3, chloride. Notice that the hip chemist kind of has to figure out here, all right, well, there's 1 chlorine next to the cobalt, and there's now 2 chlorides outside the cobalt. It's a neutral compound, so that's how you can figure out how many Cls are there. This molecule has a cation and an anion as well, but notice here how the anion is the complex ion. So this compound is going to be potassium something, all right, where the something is the anion. So cyanide becomes cyano, and there's 4 of them. Tetracyano. It's a cadmium center, all right? Cadmium here, figuring out the charge is a little bit more complicated. Cyanide is -1, and there's 4 of them, and we have 2 +1 potassiums already, so that's a cadmium +2. But there's one more thing we need to do here. If the metal is in the anion, you change its name to an 8. So cadmium becomes a cadmate. This crazy thing, potassium space, because potassium is a cation, potassium tetracyano cadmate 2. Zinc becomes zincate, chromium becomes chromate, stuff like that. If you see that, that just means that the metal center is in the anion of the compound. Here's a compound. It's got a nickel, 2 chlorides, and 2 ethylene diamines. All right. Remember, the ethylene diamine has a Greek prefix in it, so we'll use the bis thing around it. Either way, chloro before ethylene diamine. 2 -1 chlorines means nickel's +2. This one's going to be dichloro bis, parentheses, ethylene diamine, parentheses, nickel 2. And finally, this one. This one's kind of near and dear to my heart. I used to make this compound in graduate school. It was the precursor for a lot of the chromium compounds I studied. That C4H8O thing is a compound called Tetrahydrofuran. And I used to use THF, which we abbreviated as, all the time. So I put it in here just a little bit of nostalgia. Again, my apologies. Anyway, Tetrahydrofuran has a Greek prefix in it. All right, so you can't call it tri-tetrahydrofuran. That sounds weird. You would use tris, in this case in parentheses, tetrahydrofuran. Chlorine is before tetrahydro alphabetically. This is a chromium plus 3. Tetrahydrofuran is neutral. So this would be trichlorotris tetrahydrofuran chromium 3. Used to be a beautiful purple color. I wish I had pictures and stuff. Alas, that's the way it goes. Kind of cool stuff. Let's name this molecule. Now this is an iron center with 5 carbon monoxides around it. And remember that if you have carbon monoxide, it's called carbonyl. So 5 carbonyls would be pentacarbonyl. But remember, carbon monoxide is a neutral atom. So that iron right there doesn't have a charge on it. So in this case, you would just call this pentacarbonyl iron 0. This is truly neutral iron. It doesn't have positive or negative charge on it. The COs actually kind of glue themselves to the outside. So pentacarbonyl iron 0, iron with a 0 charge. It has all of its electrons and protons. Cis Platinum is an example of a compound with the chlorines at 90 degrees. It's a platinum plus 2 center with a coordination number of 4. There's both a cis and a trans form. Trans would be 180 versus the 90 degrees we have right there. Cis Platinum is still being used as an anti-cancer drug. It's based on the platinol AQ apparently, which is apparently still being used. Kind of cool. So woohoo, go coordination compounds.